Okay, so section 2.6 is special derivatives. So these are transcendental functions. And so they're not algebraic. You're just going to have to memorize what these derivatives are, okay? So there's logarithms, exponential, trig functions. So on logarithms, the properties could come into play. And if you forgot them, I'm going to review them very quickly. And this would have to do with how you write your answers, not necessarily with doing the derivative. So there were three log properties, whether it's natural log or regular log, either way they both work. But the power rule is if you have, this one will be used the most for your answer choices. If you have a log and then there's a power on the inside, you can bring that power down in front. And so what happens is you're going to have the right side and they might write it as the left side for the answer, okay? The next two properties aren't really used as often, but if you have two quantities being multiplied inside, you can split them up with addition. And this, if you have two quantities being divided inside, you can split them up with subtraction. These aren't used very often. The other key idea with logarithms is, remember, if you have natural log, remember that really means log base e of x. And let's say I said this. So if we write that in exponential form, it's really asking you e to y power equals x. And so there are these domain restrictions because remember the inside of a logarithm has to be positive. You don't necessarily have to state that restriction, but that's why it's given in the problem, okay? So sometimes you can simplify the log based on writing in an exponential form. So kind of a little bit review. It goes case by case. For most of the problems, this information isn't necessary, but you never know. All right, so the first thing we want to talk about, since we know the chain rule, this can be anything on the inside. So when you have the derivative of the natural log, it's going to be 1 over the inside times the derivative of the inside. And so I really just write it like that, 1 over u du. Okay, and everything's being multiplied. This absolute value is just technically because we have a domain restriction. Okay, so let's look at number 1. So this is our inside. So our derivative is 1 over the inside. And then we just multiply it by the derivative of 4x, which is 4. And then you do still want to simplify if you can. These 4's would reduce, so our derivative is just 1 over x. Okay? That's not too bad. Same thing with the square root. We want to change that to a power first. So our derivative is 1 over, and I am going to leave it as x to the 1/2 times the derivative of x to the 1/2 is a power rule. So bring the power down, that stays the same, and subtract 1. So if you simplify, well, the 1's going to stay. You'd have a 2, and then you'd have x to the 1/2, and then another x to the 1/2. Remember, a negative moves it down. And then common basis, you add the exponents. We actually get 1 over 2x. All right, number 3. You have to recognize that that is a product rule. So this is 1, this is 2. So our derivative is going to be 1. And the derivative of u is 2, sorry. 1 over u times the derivative of x plus 2, and then d1. I'm going to put that in parentheses so you know it doesn't change the natural log. All right, so we're going to simplify. The x's would reduce, and you get, I'll put the 2x in front. And so this is an okay answer, but we can actually simplify a little bit more. I can factor out a common x. And with the product rule, that was a pretty typical strategy. And then saying before, if we have a number in front of a log, I can actually bring that up with the power rule. So you might see this as your answer. Now, if this wasn't multiple choice, you wouldn't really know to go much farther. So just be flexible. Okay, this is probably the answer if it was multiple choice on an AP test. Okay. All right, and the last one, we've got cosine of natural logs. Remember, this is on the outside and this is on the inside. So you start by taking the derivative of the outside. So the derivative of a cosine is negative sine. The inside stays the same. And then I have to do the derivative of the inside, which is natural log. So 1 over its inside times the derivative of x. there's really not much we can do. I'm going to bring that negative in front. We've got sine of the natural log, and then it's just over x. Okay? So it's just you recognizing that it's a chain rule first. All right, so that's our recap of the log rules. So let's try these. So these specifically, we'll probably use that. So on the first one, we can start by taking the natural log derivative, or we could rewrite it with a property. I'd probably take a look at the answer choices and kind of see how they were written, but if I use, that's a product, so we're going to use the product rule of logs. So the natural log of x plus the natural log of sine. And really what this does is it eliminates the need for the product rule, okay? So our derivative, we're going to do them separately. So the derivative would be 1 over the inside times the derivative of the inside, 1 over its inside times the derivative of sine, which is cosine. So if we simplify this, we get 1 over x plus, well, cosine over sine is cotangent. Now, you'd have to see how the answers were written, but be flexible. I'm okay with this, honestly. Let's look at our next one. A quotient rule. So if we do natural log of x squared, and if I don't rewrite it with the log properties, this problem is just a lot different, but your answer will also be different. It'll be written as one fraction because you'll have to do 1 over the inside, and the times the derivative of the inside is a quotient rule. So it is a totally different kind of answer. It'll be a common denominator. These will be separate answers. But for time's sake, on the AP exam, they would have you probably write your answer using the log properties because that's just a lot faster. So our derivative would be 1 over the inside times the derivative of the inside, 1 over the inside times the derivative of the inside. And so we'll simplify. The x's reduce, nothing reduces. And so you can tell by the answer choices. If this was written as one fraction, I could get a common denominator here, or I could have started differently. All right. So let's do our second special derivative. So this is the derivative of any other base besides e. So you're going to see the log word, and then a is your base, u is the inside. Now, this is the technical way. It's 1 over natural log of a times 1 over u times the derivative of u, which is the inside. I like to reverse the order because I can spell something. If I spell 1 over u, lna times du, then I'll remember 1 over ulna, okay? So it's really your choice. This is the way you see it written in books, but this is the way I memorize it because really I can, if it's being multiplied, I can just put that u in front. And I just don't write u prime, I just say du because I always say du, derivative of the inside. So here's my a, here's my u. A is always a number, that's why it's the base. So if we want to take our derivative, and these are pretty straightforward, there won't be a lot of simplifying either. You've got 1 over the inside u, so 4x plus 1, the natural log of a, and then times the derivative of the inside, which is 4. And so really all I can do is put the 4 on top. This is really just you memorizing it. And this really could be a multiple choice question because you don't use this derivative a lot, so a lot of people are going to forget it by the end of the year. E will be used a lot, okay? The nice thing about E, and I believe it's the only one, is because of the way the curve works, the slopes of the E curve, when I go to do my derivative, are actually the same. So it's the only function that is its own derivative. You still have to multiply by the derivative of the exponent, but that's because it's a chain rule. So our derivative, we go e to the u. So it stays the same, and then I multiply by the derivative of the exponent. And then we always just write that coefficient in front. Okay? I know I did it quick, but it is pretty quick. All right. My next one, I'm going to start out. It's e to the u stays the same. And then I'm going to write this as x to the -1 because I know I have to take the derivative of that exponent. So I want to use a power rule. So bring my power down and subtract 1. So I'm going to write this nicer. I get -1 over x squared. I'll just write an x to it. And then really, like you'd be able to match this out, but they're just going to put that on top. So negative e to the 1 over x all over x squared. That's what you would see. And my last example, that's just a number, so that stays. So the 2 stays multiplied, e to the u stays the same. Then I'm going to rewrite this so I can do the derivative. So bring my power down, subtract 1. So my 2's would cancel out. I'll go ahead and do that. And we get e to the root x, and then this is a negative power. I'm just going to write it over there. All right, the last special function, once again, it's a to the u. So remember, a is a number, so it'll be like 5 to the x, okay? So it's a to the u, ln a times du. And there's no easy way to memorize it, but it just, to me, rolls off the tongue, but I've been doing this a long time. So here's my a, here's my u. So our derivative is, notice it stays the same, okay? But there is more to it, so I can't just say it's its own derivative, because it's not. So a to the u times the natural log of a, and sometimes you'll see this in parentheses, times the derivative of the exponent. So it kind of follows the exponential derivative idea, but it's a little different. And this has to do with taking logs and stuff like that. There's a lot of math going on behind here. Now, what you might see, and it really depends on the derivative, but since this is a number, let's go ahead, I'll show you. We want to kind of reduce the number of terms we have. So I can actually put that 3 in front. And then since that's all just a number, we can kind of think of it together. And then they might use that as a power. I don't know. It really is just being flexible if this is multiple choice. So that would be 5 cubed, which is 125. They're all really good, to be honest. All right, let's look at y, the next one. So it's 1/4 a to the u, okay? So our derivative is a to the u times the natural log of a times the derivative of u. And so this is like e to what power gives you 1/4. They're not going to separate that, so this is probably what you're going to see. Okay? And I'll go ahead and put that in parentheses because it's bothering me. Okay, so now we're going to get a little bit more complicated since you know the basic rules, and we're going to mix them all up. Okay? So let's look at our first example. We've got this quantity to a power rule. So remember, this is on the outside. This is going to be a chain rule, and this is on the inside. So our derivative, we start with the power rule. The 3, the inside stays the same, and we subtract 1. Then we multiply by the derivative of the inside. So these are being added. We take them separately. So e to the x is still e to the x, and the derivative of 3 is nothing. And so really, the only thing I do is I just put the 3 and the e together. Factored form is the best. All right, this sine is on the outside. E is on the inside. So we start by taking the derivative of sine as cosine. The inside stays the same. I don't use parentheses. You can if it bothers you. Times the derivative of the inside, which is e to the x. Now, those don't go together. This goes in front. The inside, remember, cannot change. All right, this is on the outside. This is on the inside. So the derivative of natural log is 1 over the inside times the derivative of the inside. So 1 over the inside times the derivative of the inside we do separate. X is 1, and e to the x, its own derivative. So we get this on top and this in the denominator. And remember, because we're being added, we cannot reduce anything. Only if they were being multiplied. They're not. All right, y, we can't avoid the next one. We have to do a quotient rule. So low d high minus high, and then d low is e to the u times the derivative of the exponent. All over, I'm going to write it e to the 4x squared. Okay, so let's simplify. We get e to the 4x minus, I'm going to put the 4 in front, and I'm going to just leave this alone for a second. I'm not actually going to multiply that out. And if you look in the numerator, you can kind of see why. So I can factor out an e to the 4x, but since they all have those terms in common, I'm just going to show it being reduced. So I'm going to take out an e to the 4x on that term, an e to the 4x on the second term, and one of those e to the 4x's. So I'm left with 1 minus 4x all over one of them. You don't have to factor out if you can see that it does, okay? It would have been this, just in case you don't see it on top. All right, our next example is a product rule. So 1, d2, that's an a to the u rule. So a to the u times natural log of a times du. 1 d2 plus, these are always so long, 2, and then d1 is a power rule. Now, we have two terms here, and I know it's hard to see because they're not side by side, but with the product rule, you want to try a common factor. So both terms have a 10 to the x squared. I can take out, I don't have a 10 there. I can take out a 2, and I can take out an x to the 9th. Now, those can be in any order. I'm going to put these in parentheses. So if I take out, actually, I'm going to write this nicer. Let's write it down here. And I know it is hard to see. So y prime, we're going to take out a 2x to the 9th and then 10 to the x squared of both terms. So what we're left with, I'm going to take that one out, take out 9 of those, and take out that. So I am still left with an x squared, natural log of 10, because that's left, and that's left. Plus, I'm going to take out 10x squared, 9 of those, and divide by 2. So I'm left with plus 5. This might be the multiple choice answer. There's not much we can clean up, so I think it would have been in factored form. They might just actually leave the original one just to get you to match it out. Okay? All right, this is our hardest one. This is really a challenge. Okay, so first thing is I'm going to rewrite this. So this is really the secant of the natural log 4x squared plus 2 all squared, okay? They try to sneak that in on you, but I like to see it. So really what's happening is this is on the outside, and we have a bunch of chain rules on the inside. We have one inside here, one inside here, okay? This is going to be tricky. So our derivative, we start by doing the derivative of the outside, which is a power rule. So we bring the 2 down. All of this inside stays the same. And we subtract 1. Now, I'm just going to do the derivative of the inside. So this is the outside, and this is all the inside. So the derivative of secant is secant tangent. So I'm going to write it down here. So we've got secant tangent. The inside of that stays the same. Times the derivative of its inside once. So that's a natural log. So it's times 1 over the inside times the derivative of that inside, which is 8x, and then that went to 0. So now there is a lot going on here. There's actually not a lot you can clean up. I've got this 2 in front, but I can also reduce that. So 2, and if I take both a 2 out of there, I'd be left with 2x plus 1. And I saw the 8 on top. So I'm going to just write this nicer, just this part. 8x over 2x squared plus 1. And this would get multiplied by all of that. So if I write my final answer, it's really long though, we get this. I'm going to write it in pink. Times that. Notice I actually have one here and I have another one. So we're going to say that this is, we'll say squared. And then times tangent. Yeah, this is a lot, I know. Okay. Well, if you are confused on the last one, definitely is not an AP quality. Like that is very time consuming. Stick with the others and you should be fine, okay?